Have you ever just stopped and wondered why things happen? You know, why an ice cube melts in your glass, or why a fire roars to life, but you never see the ash turn back into wood? Well, turns out there are these powerful, invisible rules running the entire universe, and today we're going to crack the code on them. We're diving deep into thermodynamics. And hey, don't just take my word for it. The one and only Albert Einstein was absolutely convinced that thermodynamics was the one theory that would, stand the test of time, forever. When Einstein says something's that fundamental, you know we're talking about the very bedrock of reality itself. So this gets us to the heart of the mystery, right? All around us, things just seem to go in one direction. You drop an egg, it scrambles. You spill a drink, it spreads out. These things happen spontaneously. But what's the cosmic law that says it has to be that way? What's this hidden rule that's calling the shots for the entire universe?
I mean, really think about it. If you open a bottle of perfume, the scent fills the whole room. You'll never see it just decide to go back in the bottle. A log burns down to ash, but that ash never rebuilds itself into a log. And your coffee cup always warms your hands, never the other way around. These are all one-way streets. And today, we're going to figure out what's directing the traffic.
Okay, so before we start our investigation, we need to set the scene. In the world of thermodynamics, we always talk about a system. That's just the little piece of the universe we're actually looking at. So if we're watching that ice cube melt, the ice and the water are our system. Everything else, the glass, the table, the air, you, me, that's all the surroundings. Simple enough, right? Now, these systems can interact in a few different ways. You've got an open system, kind of like a pot of boiling water. It's letting out heat, which is energy, and steam, which is matter. Then there's a closed system, like a sealed bottle of water. You can heat it up or cool it down so energy gets through, but the water is not going anywhere. And finally, you have an isolated system. Think of a perfect thermos. Nothing gets in, nothing gets out. Keeping this straight is going to be super important.
All right, detective hats on, let's look for our first clue. The most obvious suspect for why things happen is, well, it's the natural tendency for everything to want to get to a lower energy state. It just makes sense, right? A ball rolls downhill, not up. It feels natural for things to end up with less energy than when they started.
And in chemistry, we've got a name for this prime suspect. It's called enthalpy. We write it as a triangle H, or delta H, and all it really is a way to measure the heat that's either coming into or flowing out of our system. It's like tracking the energy budget for a chemical reaction. So you've got two main flavors of this enthalpy change. If a reaction gives off heat, like a campfire warming you up, we call that exothermic. And because the system is losing energy, its delta H is negative. On the flip side, if a process sucks in heat from its surroundings, like one of those instant cold packs, that's endothermic. The system is gaining energy, so its delta H is positive.
Let's look at the evidence. Case file number 1, making water from hydrogen and oxygen. This reaction is, well, it's famously explosive. It definitely happens spontaneously. And just look at that delta H value. It's a big, fat negative number. It's dumping a ton of energy. This is Exhibit A for our downhill energy theory. Okay, next up, case file number 2. The Haber-Bosch process for making ammonia, super important for all the fertilizer that grows our food. And look at that. It happens spontaneously. And surprise, surprise, its delta H is also negative. It's releasing heat. The evidence is really starting to pile up, isn't it? So the case seems pretty open and shut, right? The driving force for a reaction must be this drop in energy. Spontaneous things happen because systems are just rolling downhill to a cozier, more stable, low-energy state. It's simple, it's intuitive, it makes perfect sense. But you know what they say, if it seems too simple to be true, it probably is. Is that really the whole story? And here it is, folks, the plot twist. Because we're about to look at a reaction that's going to completely blow our nice, simple theory right out of the water.
Get a load of this. We're looking at a reaction to make carbon disulfide. Now look closely at that enthalpy change. It's positive. This reaction actually gets colder as it goes. It's pulling heat in from its surroundings. In energy terms, this thing is rolling uphill. According to our first theory, this should be impossible. It should never happen on its own. And yet, it does. It happens spontaneously.
Whoa! So this one single reaction just proved that our whole case was incomplete. The drive to lose energy, that negative enthalpy, it's definitely a big deal, but it can't be the only thing calling the shots. There has to be something else, another force at play here.
So if it's not just about energy, what is this other, more mysterious force that's pushing things along? Well, it turns out to be one of the most fundamental ideas in all of science. The universe has an unstoppable drive towards messiness, towards disorder.
And this drive for disorder has a name: entropy. We use the letter S for it. Basically, entropy is just a measure of randomness or disorder. Think about your bedroom. There are a million ways for it to be messy, right? Clothes on the floor, books everywhere. That's high entropy. But there's only really one way for it to be perfectly tidy. That's low entropy. The more possible arrangements something has, the higher its entropy.
Here's the perfect analogy. Imagine a brand new deck of cards, all sorted by suit and number. That's a state of perfect order, super low entropy. Now, what happens when you shuffle it? Just once? Boom. It's a jumbled, disordered mess. Why? Because there are trillions upon trillions of ways for the cards to be mixed up, but only one way for them to be in that perfect order. It's just probability.
And that, right there, is the universe in a nutshell. It's constantly being shuffled, and it naturally, automatically moves towards the most probable state. And the most probable state is always one of greater disorder, of higher entropy. This is the second great driving force of nature.
Okay, so we've unmasked both of our culprits. We have the drive to lose energy, which is enthalpy, and we have the drive to increase disorder, which is entropy. Now it's time to bring them together and deliver the final verdict on what makes things go.
So here's the big reveal. Spontaneity isn't just about one thing. It's a cosmic tug of war. On one side, you have enthalpy, pulling things towards lower energy. On the other side, you have entropy, pulling things towards more disorder. And whoever wins that tug of war decides which way the reaction is going to go.
Let's break down how this works. If a reaction releases heat and creates more disorder, like a fire, well, both forces are pulling the same way. That's an easy win. It's always spontaneous. Now, what if something absorbs heat and creates more order? Well, that's fighting both natural laws. It's never going to happen on its own. The other two are where it gets interesting. Freezing water, for example, releases heat, but it also gets more orderly. So it only happens when it's cold enough for the energy factor to win. And melting ice? That absorbs heat, but it creates much more disorder. So it's spontaneous only when it's warm enough for the disorder factor to take over.
And that's it. That's the secret. These two forces, this push towards lower energy and this pull towards greater disorder, they are the fundamental rules that decide the direction of literally everything that happens, everywhere in our universe. From a simple chemical reaction to the life and death of stars.
Which leaves us with one last kind of mind-blown question to chew on. If the entire universe is on an unstoppable one-way trip towards maximum disorder, then how in the world is it possible for something as beautifully complex, structured, and orderly as life to even exist? That is a puzzle for another time.